Today, so I think early in the week I said I was going to do objects, but I forgot I'm going to do objects next, visual object recognition next Friday. And so today, two different things. So the first thing is to go over I talked about the smoothness constraint, but I didn't explain it. So I'll kind of go over that as a way of solving the aperture problem, and then also talk about an old computer vision thing called line processes. But the reason I talk about that is because if you're kind of smoothing, one of the things that happens is how do you actually see the edges of objects or overlapping objects? And that's actually a real problem for the visual system, not just for computer vision systems. So I'll talk about that a little bit, and then we'll change over and talk about perception of depth perception. So perception, yeah. So it turns out there's a lot of different things that can tell you about depth. And so we'll just sort of go over that in a general way and then talk about stereo, because you probably know that if you have two eyes, you can see two slightly different views of an object, and that gives you the ability to calculate how far it is away from you. It turns out stereo is actually not even the main depth perception in a way. It's just one of many, but we'll talk about how that works. And there's kind of an aperture problem there too, so we'll go over that. So if we go back to the dreaded gradient model, remember the idea was we assume that E, which is the brightness, we assume that the brightness of an object doesn't change. So that's our first assumption. My good green is, let me get a new green. Okay, so that's our first assumption. We do some calculus, and then we end up with this equation, which is that the change in the brightness when you move in the x direction in the image at a point, multiplied by the velocity in the x direction, plus the change at a point in the image when you move in the y direction, multiplied by the y velocity, plus the change in the brightness to the next time point is 0. So what is the dx, dy, and dx, dt mean? So what that means is if you have a certain direction and speed, you can put that in a Cartesian coordinate system, and this is the dx, dt. That's the x component of the velocity, and this is the dy, dt. So just sort of demystify it. It's just the Cartesian coordinates of the direction and speed. So that's these two things. And so those are the unknowns. That's what you're trying to figure out, like what direction is something moving. So these guys are the unknowns. There's two of those. And then these guys are the data. So these three are the data. So those are the things you can measure from your video frames, or from your successive 2 time points of data coming from your retina. So the problem was there's two unknowns, and so when we looked at how that problem works, if we just take a very simple case, like 2 time points on a small grid, if we've got, say, like a pixel here, and then next time the pixel is there, so this is like time n plus 1. If we run through this calculation, what we find out is that if the pixel moves in that direction, that will satisfy this equation. if you look at the change in the brightness in the x direction, change in the brightness in the y direction, change in the brightness over time, that will come out to 0. But unfortunately, if you move this guy up, so instead of moving it to the right, move it up, it also works. The equation also works. So, and that's the aperture problem. You can't pick up when you're just calculating these small changes in the image in the x and y direction, and over time you can't pick up this essentially this slip that's parallel to the edge, parallel to an edge. So how do you solve the problem? So you solve it with what's called the smoothness constraint. The smoothness constraint. And what does that mean? That means we have a grid of estimates of the velocity. So this is a grid of estimates of the velocity. And there's all different, so at a point, there's a choice. So, say like this point right here, it could be that way or it could be that way. So we'll just put those in dotted lines. So it could have been that way, but it also could have been that way. We don't know. All those are possible. So if you now say, let's solve across this whole mess, like these 16, and find a solution that is the smoothest. And so what that means is that there's going to be multiple alternate solutions, but if we find one where the velocity sort of changes smoothly across space, like this, something like that, doesn't change too much. That's a smooth velocity field. So basically what the smoothness constraint is, before I write it out in equations, is just find smoothest in terms of velocity, velocity field across space. Because at any given point, there's multiple ones. But what we can say is if we look across space, we'll solve at the same time for all those guys and find out which one is the which solution is the smoothest across space, and that one is going to be a good one. So find smoothest velocity field. So why go over this? It sort of seems like it's sort of obscure calculus, but the reason to go over it is because it's dealing with a real problem. And one of the things that you see if you read the literature, if you read some computer vision guys, they're doing something. If you read the people who are studying nervous systems, they're doing something else. They're kind of working on the same problem, really, but they're phrasing it in very different ways. And so one value of this is just to see how a given sort of like more general problem is approached in completely different ways, and to sort of like back out and really get a better understanding of it. So what's the equations? So the first thing is we want to. So how do you find the smoothest velocity field? So now we have to sort of like state it a little more generally. And what we do is we minimize two things. So we minimize error because we want to, if this turns out to 0, that's no error. And so we want to minimize error and non-smoothness. So there's two different things to minimize. And so we have to first write out like what is the error. So the error is basically, so we start off with the error. So what's the equation for the error? Well, the equation for the error is the extent to which you don't follow this equation. And so that should be 0. And so if we sum across all x and y, like this x and y patch, and we just sum that thing. So that thing is just, it's supposed to be 0. So, but we can calculate it, at each point and add the whole thing up. across space. That's what this integral means. So here's dx dt plus the change in the brightness in the y direction times the y velocity, y dt plus the change in the brightness over time. So that thing should be 0, so the bigger it is, the more the error is. A lot of times when we're minimizing things, we square things, and why do we do that? Because then if that number is supposed to be 0, but if it was negative, that's an error. If it was positive, that's an error. So if we square it, it's going to always be positive. And so we can minimize the squared error, and that's a simpler problem. And then we're summing across. So that's basically how you calculate the error. So basically you go to all these things and see the extent to which it doesn't equal 0, add the whole mess up. Square it, and then add the whole mess up. And you get an error. It gets bigger as your velocity field is less consistent with the data. So that's the error. Then what about the non-smoothness? So we want to minimize that. So we want to make it smoother. So our equation is for the non-smoothness. And this equation, so as we start to get more and more derivatives, a lot of times what people do is they call this guy u and this guy v. So we don't have to, because we might want to know the change in the velocity. So what is the change in the velocity, like the change in the x component of the velocity? So that would be something like, here's the x component of the velocity, and there's the y component, and here's the x component of the velocity and the y component. So we can look at what is the change in the x component as we go across space. So this thing is already a derivative, the dx dy velocity, but we want the change in the derivative, and so we'll just call it a u and a v so we can take another derivative of it. But that's, just think of it very concretely. All you're doing is looking at how does the velocity x component change when you move in the x direction or in the y direction. And so our equation for the non-smoothness is the change in the x velocity, that's u, when you move in the x direction. That's what I drew here. But there's 3 other possibilities. So and then we square that because we want to always have a positive number. So then we're going to have the change in the x velocity when you move in the y direction. So that would be like seeing how the x component, let's just draw it out. So that would be there. So that would be, here's another vector there, and there's the x component, and there's the y component. And so we could look at how does the x component change when we go up here. That's the second one. And then there's 2 more. You can see what the 2 more are. So plus the change in the y component when we move in the x direction, plus the change in the y component, that's the v. Sorry, did it backwards. Man, I'm not a mathematician. U, v. Change in the y component when we move in the y direction. And so all those guys are squared to make them positive, and then we sort of sum across all space. And so that will tell us how not smooth it is at each point. And then when we sum across all space, it tells us how not smooth it is. And so all we have to do is just find a solution that minimizes these 2 put together. So what does that actually look like if we sort of run it? So, say we've got a video image like this, and there's a little patch on it like that, and the patch is, moving in some direction. If we just take a line across that, what is it? Just to make it a little simpler in 1D, what does that look like? Well, it looks like and let's assume, there's a little noise in the video. It's not a perfect bright thing with no jiggles in it at all. It's got a little, there's a little sort of noise in the background. So what will that look like? If this is the brightness, so this is the brightness, it'll look something like this. And then there's an object. It's got a little speckle on it. And then here's the rest of the object. So when we calculate a motion field using the smoothness constraint, what do we get? Well, we're going to have to say this is like u, so the velocity in the x direction. So what's the velocity in the x direction? Well, it's going to try to be smooth as possible. So, but also sort of like, respecting the data. And so what is the error? Well, the error is it's all these little offsets from the actual data to our smooth solutions. Finding the smoothest solution. So so the velocity will be off because we found a smooth solution instead of one that had like a sharp edge in it. So that's how these equations actually work. So we pay a little penalty, we get a little bit of error near the edge of the object, but we still solve our problem of having two unknowns, and we end up with a solution. So the problem with this is, well, what happened to the edge of the object? It's kind of smooth. So what this look like? If we solve that, what would it look like in 2D? It's going to look something like, in the middle, the velocity vectors are going to be big, and then they'll sort of like start to fall off, and then they'll fall off and get smaller and smaller, and so you'll see a big blur across the object. And so as you go like that, and then what happens if there's like two objects? What if you've got, this happens all the time in the world, and you have to be able to deal with it. If you've got one object moving that way, and say there's another object that's going that way. Yeah, that's not uncommon. Stuff's constantly sort of moving around like that. How do you deal with that? It's just going to be a big, massive blur. And so one solution was something called line processes. Now it's kind of like just a little weird cul-de-sac of computer vision, but it's a real problem that the real visual system has to deal with. If it's got some large receptive fields in MT, and it's looking at these big, it's blurring out the data, how does it deal with overlapping objects? Because that happens all the time. If you've got an overlapping object, you still have to be able to calculate what the motion of that object is if you want to grab it, for instance. And so what you can do is you can add another thing to our minimization. These are called, line processes. And the way this works is we've got this situation here. Now, so here's our data again. So there's like low velocity, and then in real life, high velocity, and then you reach the edge of the object, low velocity. What if instead we allowed there to be a discontinuity occasionally for some cost? So then what we could do is we could fit this, and then there'd be a discontinuity here, which we kind of have to pay for in our accounting, and then we could fit the data better with just, say, two little discontinuities. So that's what in words, that's what a line process is. So now we want to minimize more things. Minimize. So we want to minimize error, and then we want to minimize the non-smoothness of our solution. And then we want to minimize a penalty for an edge, penalty for a discontinuity. But then the fourth thing, which is why it's called a line process, is we want to minimize want to minimize non-collinear. And what does that mean? So that just means if we say we've got, well, let's put a discontinuity in here. And so if you put a discontinuity in there, that allows us to fit the data better. It allows us to get sort of more smoothness and more smoothness and less error. But say we also have a discontinuity like that. And so what we're going to say for our non-collinear business is you have to pay more for a discontinuity like that. Whereas if you have a discontinuity that goes along an edge like that, that's better. So that guy's a collinear discontinuity. It's allowing a cut in the velocity field going this way, but this thing is not good where we have a discontinuity that is not along a line. So that's why it's a line process. And so what that will do is that will allow us to sort of introduce these discontinuities here that allow us to fit the data better. Now, is this the way the brain does it? No, the brain doesn't do it this way. But it's just a way of stating the problem. So the problem is we have to, it's a real problem for the brain. MT neurons have to, how do MT neurons do the smoothness constraint? They do it by having a receptive field that looks across a bunch of different parts of the world. And when it does that, it sort of blurs out, that neuron it doesn't really know exactly where the motion is in there. It just gets some signal across that whole mess. That's basically smoothing. But then the problem is objects are sort of overlapping and moving, and so we've got to deal with, where are the actual edges, in the object. So V1 knows where the edges are, but it has the aperture problem. MT doesn't really know exactly where they are, so can it go back to V1 and ask something like that? So it's a real problem in order to deal with any kind of realistic scene, which will have multiple objects in it moving in different directions, overlapping each other. So this is just one sort of like strange computer vision way of stating it, but you can sort of see what the problem is. We could sort of say, well, allow discontinuities in our smoothness, but we like it when they're along a line. So that's a line process. Okay, so that was just going over the gradient things that people did with the gradient model, after they initially described it around in the 1980s. Okay, so and it's an interesting thing. We still don't really know how MT does this. How does MT figure out where things are when there's two objects in the receptive field, for instance? And it's even worse when you get up to MST because it's looking at like 20 or 30 degrees. So if you've got a rotating object and another rotating object, which happens all the time, how do you actually sort of parse that and figure out that there's actually two objects there? So these are all problems that are being solved, higher up in the cortex. We don't really understand at the neural level very well how those work. But this is more just like a statement of the problem. Okay, so now let's completely change over and talk about depth perception in general. So depth perception involves a lot of different things. Not just stereo. And what are some of the things that you can use to tell how far away something is? So what is the general problem? Let's just state the problem. So the problem is you want to go from sort of 2D to 3D. So basically, you've got an image on your retina or on your video camera. And the problem is, at each point in the image there's some brightness, maybe an object, and the question is how far away from it are you? That's not in the video image. The video image just has like a two-dimensional map of brightnesses. And so this is something you have to calculate to try to figure out how far away something is. And all animals need to do this. Frogs need to do this. Chameleons need to do this. Bugs, flies need to do this. So how far away is something? There's a lot of different things you can use to calculate that. And artists have known about this and sort of intuitively figured out how to do some of these things in order to make a painting that looks like it's got depth in it. And one of the very basic ones is just the sharpness. So the sharpness of an object, how blurry it is. So what happens at a distance, there's a little smoke or fog or something in the air, and if you look at contours in the distance, they're not as sharp. And so you can tell the depth of something in your visual system by just looking at sort of how, on average, how sharp the image is. That's a very important cue for depth. But contrast is another one, because as you go off and you go through more haze, things tend to be less contrasty. And this is so natural, your system is so used to seeing this, you can't see it. You have to really kind of like take a picture of something, like take a picture of the mountains with a car in the foreground, and then just actually look at it carefully, and you'll see that the contours on the car are more contrasty than the contours on the image in the background. So that's a very important cue to how far away something is. Another important cue is overlapping, occlusion. Occlusion. So obviously if you've got an object like this and another object, and you can sort of see that, you recognize that that's a square, that tells you how far away something is. And then another one that we talked about already when we talked about blob cells is shading. So especially when you look at a cylinder, which is of course all there is in the world of 1980s computer graphics. So if you've got the sun here, what's going to happen is this part is going to be bright and it'll fall off, and the top will be very bright because the sun's sort of shining down on it. And so that method of just analyzing the shading is a way of telling the depth of the object on a kind of a small object level at the scale of an inch or something like that. So then there's perspective. So as things get closer to you, they get bigger. So if if we make a drawing of a cube, so here's a cube. So we'll sort of make lines off to our vanishing points. So if I draw that cube in perspective, what it looks like, something like this. That goes off there, and that goes off to that guy. So if you look at, there's subtle differences in the angles between the different edges of an object, and what's causing this? Well, what's causing this is that the corner of the cube here is closer to your eye, and so it's going to be bigger, and the further away parts of the cube are smaller. So your system is quite sensitive to these subtle changes in the relative angles of objects that indicate how far away something is. So that's another cue that doesn't require stereo. And then I can't remember, there's two N's in accommodation. Yeah, accommodation. So visual neuroscientists say accommodation. What do they? That doesn't seem to mean anything. It just means focus. So you can use the focus. Now, how do you focus? Well, you focus by tugging on your lens with some muscles. fine focus. So most of the focus comes from your cornea, because your cornea is like a lens. It's got a smooth sort of curved surface. That focus, that's the main thing that focuses the light on your retina. But the focus, the fine focus is done by the lens, and so some muscles will just sort of tug on the lens and cause it to change shape, and that will change the focus. So what you can do is you can look out at something and then focus on it. Now, that's kind of a whole problem of its own. How do you focus? Well, somehow you have to tug on the lens a little bit, and then you have to go and process stuff in your visual cortex or somewhere, superior colliculus, and then decide that was, on average, pretty sharp. And so then tug a little bit more, and then analyze it up there, and you say, that was sharper. So you have to somehow estimate how sharp the thing is. That's kind of a complicated thing, and then feed it back to the muscles that are tugging on the lens. But so we didn't say like how you do that. That's a whole problem, problem of its own. But once you've done that, then what you can do is just read out how much the muscles are pulling, and that will tell you how far away the object is. So then you take the signal of like, what was the internal signal that we sent out to the muscles to tell them how much to pull, and then feed that back into the depth system. So that's yet another completely different, why this is biology. So you don't throw away anything. Like you can use focus, you can use like sort of shape of things, you can use shading, you can use, overlapping, contrast, sharpness. All these things are used in order to actually figure out how far away something is. This is the way like chameleons do it. So if you've probably seen a chameleon, they have eyes and they're looking in they're disconcertingly looking in different directions, looking around for bugs. And when they see a bug, what they do is they just look at it with one eye, not stereo, look at it with one eye, focus on it, and then read out, how much muscle power was used to do that focus, and then that is proportional to the depth, and then just decide whether they're going to try to eat that bug, because their tongue is only a certain length, and if it's beyond the length of their tongue, they're not going to hit the bug, and so why bother? So you got a sticky tongue, sort of like shoot out with a little bone in it, so you can get the fly and get it back in. So that's another thing, and then finally stereo. So stereo basically is you've got two eyes looking at the same object. So you got two eyes looking at the same object, and so they have slightly different viewpoints. And you can use information about those slightly different viewpoints. But even stereo has got like subparts to it. So let's subdivide stereo. So stereo generally means like look at things through two eyes. And, first there's classic stereo where we can see the same thing in the two eyes, but from slightly different viewpoints, like a stereo viewer where you look through a stereo viewer, it gives you a very convincing feeling of 3D. But it turns out all the time, you don't realize it, all the time, you also have double vision. So the way to demonstrate, you can't see it unless you actually sort of really do something. So say I focus across the room. So I focus across the room on the Dalai Lama out there, and now I bring something close into my face like this, but don't focus on it. Just look at what's across the room. Now pay attention to what that object that's close to me looks like. And if you go back and forth between your two eyes while continuing to focus on the Dalai Lama, you can see that object that's close to you is it's like a couple inches apart. The left and the right eye image of that object are way far apart. That's called double vision, because it doesn't look like a single object. It looks like two objects. And so this is constantly happening. Every time you look across the room, anything that's close to you, your hands, for instance, are in double vision. You've got two copies. So it turns out this can be used. Regular stereo is not doing that. Regular stereo is like, fusing the object, the left and the right eye images of the object together very closely. But double vision can be used. And you can even use what's called monocular occlusion. So say you're looking at something. Say you're looking at an object that looks like this. This is depth. And so here's, here's two eyes looking at it. Somebody in the walls. So here's two eyes looking at this object. So what's going to happen is this eye can see here and then to here, and then this eye can sort of see here and here. So this little piece of the object, only one eye can see it. And same with this little piece of the object, only this eye can see it. You can use that information to tell how far, what the depth of an object is. So now that we've got that down, let's finally talk about classic stereo. And so this is what you typically think of as stereo when you talk about stereo vision. And so classic stereo. So it turns out, what are we going to do stereo with? Well, we got simple cells and we got complex cells, and so we have a stereo aperture problem that the visual system needs to solve. And so before I talk about the stereo aperture problem, like if you read any textbook on stereo, they might talk about, David Marr and the idea of that came out of the MIT AI lab on how we might try to calculate stereo using, computer algorithms. That's not actually the real stereo aperture problem, but I'll just go over that quickly to sort of see what that is. So imagine you've got 4 dots out in the world. Say that's actually where they are. They're on a plane. And then we're looking at that with our eyes. So I'm going to exaggerate how far apart the eyes are so that we can sort of see the effects. So 2 eyes are looking at this. So if we project where these things go into the eyes, what's going to happen? So this guy is going to go into the eye and then get refracted a little bit, and this guy is going to go into the eye and get refracted a little bit, and same with this. So these will basically go in and they'll be projected into the retina, into these 4 places on the retina. And then the same thing will happen in the other eye. I kind of like got that. Let's make the lens. So this is going to go there, and there, and there, and there. So we've got 4 dots on the other side. But now the problem is there's other places the objects could be. And so in the computer vision literature, this was called the false targets problem. So if we trace all these lines out like that, turns out there's 16 places where the objects could be. So, the object could be, there could be an object there, or there, or there, or there in depth, or there, or here, or here, or here, or here, or here, and there's one more. It's going to be this guy. I drew the lines a little bit too far apart. This guy intersecting this guy. Okay, so those are supposed to be straight lines. Okay, so there's 16 places where it could be. If all you know is you got 4 spots in this guy, 4 spots in this in this eye. So this is left eye and right eye. Who knows? Which one matches with which one? So this was called in computer vision, this was called the false targets problem, or the false, false match problem. So we don't know, and this especially came from, if you've probably seen those random dot stereograms where there's no structure and there's just a bunch of dots, and you displace some of the dots and it makes it look like it's in 3D. So that's kind of where this kind of research came from. What is the actual problem? So what is the true, the real stereo aperture problem? There actually is a stereo aperture problem, and so what is the problem? Well, it comes from our simple cells. So say we have a simple cell like this. Say it's got 4 fields. So it's got put on, off, on, off. Now I drew that just as a single thing, but remember, we've got 2 eyes. So we have another copy of that. So there's another copy over here. It's generally going to be more or less on top of the other eye. So we have, so this is a simple cell. And then this is the right eye, say. Right eye, and this is the right eye receptive field, and this is the left eye receptive field. So how would you do this experiment in practice? Obviously, normally it's hard to vary what's going into the left and the right eye, and so you'd have to put some mirrors in and have 2, like say have the person or the animal looking straight ahead. They look into 2 mirrors, and those 2 mirrors go to two different video displays. And so then you can independently change what's going on in the left and the right eye and see what happens. So in order to test, as we move things around in the left eye or the right eye or both of them. And so you can immediately see what the problem is. So the problem is, this is a simple cell. It likes things that get brighter in the on fields, and it likes things that get dimmer in the off fields. So say we put a spot on. Well, there's multiple combinations of things that could activate this cell. So if we put a spot in the on field in the right eye, and then in the first on field in the left eye, that's good. But it would also be good if we put a spot on in this on field in one eye and that on field in the other one, or this one and that one, or this one and that one. So there's 4 different combinations of bright spots that could cause that cell to become active. So we can draw that out on a graph here. So this is basically, make it a little bigger. So this is basically the x distance in the left eye and the x distance in the right eye. And so what would, if we just tested with a single spot, what would happen? We would, if we came in from this side, we would have a response, an on response, and then there'd be an off, and then an on, and then an off. And the same thing would happen, that's for the left eye, same thing would happen in the right eye. There'd be an on response, and then off, and then an on response, and then off. So what if we did 2 things at once? Well, then what you're going to get is you'll get 4 different combinations of x distance. This is our x distance, perpendicular to the orientation selectivity. So there's 4 possible those are the ones I just said. So you have bright spot here, bright spot here, bright spot here, bright spot here, 4 different combinations. And so any of these combinations, could, activate the cell. So the cell is kind of ambiguous. It doesn't really know like what the offset is. And one thing that we didn't say is, what is the difference? This is, I should back up to the very start. So, stereo concept. So what is our basic effect of looking at an object with 2 eyes that are separated from each other horizontally? So, so the basic stereo is that, objects change position slightly in horizontal direction with different depths. So that's how stereo works. So and you can confirm this by just looking at something and then say, looking at a close object, looking at the left and the right eye vision of it, looking at a far object, left and right eye vision of it. You can see objects will move slightly in the horizontal direction proportional to depth. So that's fundamentally, so we want to measure like what is the little offset between the left and the right eye. That's our goal. So this would be the case where we used, say, a bright bar in the left and the right eye. So say we put a bright bar in the right eye, bright bar in the left eye. But now you can see what the problem is. What's going to happen if we use a dark bar? And what's going to happen if we use a dark bar in one eye and a bright bar in the other eye? So there's like, a zillion combinations. So say we use a dark bar in the right and the left eye. What if we used a dark bar in the right eye and a light bar in the left eye? Or what if we used a dark bar, a light bar in the right eye and a dark bar in the left eye? All those things could happen in real life because your eyes just looking out at the visual field, and there's dark stuff and light stuff, and your eye, the receptive fields are somewhere. All those possible combinations are there. So what's going to happen here? So here, there's going to be no response as we move in the x direction, and then suddenly there's a dark bar, so it's going to like that, and then no response because that's on, and so you end up with something like this. And so what is that going to do? That's going to cause activation at these points, different than before. So it's different than there. And what are the other possibilities? Well, we could have a bright bar in the right. So here's a bright bar in the right like that, and then a dark bar in the left. So that one's going to have no response in the on field, and then the off field like that. And so yet another possibility. So it would cause activation when the 2 things are in this location. And there's yet another possibility, which is dark bar in the right, and bright bar in the left. So it's just a unholy mess of all these different possible matches depending on light and dark. So how on earth does the system solve this? Well, one of the things that's an advantage of a complex cell is that a complex cell doesn't really know where the bar is. It doesn't really know whether it's light or dark. So if we do the same test with a complex cell, except now using a stereo stimulus. So here's a complex cell. Below the line. This is what I should have started with, the stereo concept. How does stereo actually work? So if we look at what happens with a complex cell, you can find a complex cell that does what we really need it to do. And so here's the distance in this direction, in the left and the right eye. So this is, let's label this correctly. So this is the right eye x position, and here's the left eye x position. Okay, now I should have put that on before. So if you look at this, a complex cell, you can find a complex cell that has a response that looks like this. And so what is that? That's so that's zero disparity. It's zero disparity, but we're changing position. And so if we look at this picture, what's going on in this receptive field picture? So if we draw receptive fields here for our left and right eye, what's going on here is that, what does this graph mean? What that graph means is, if we put a bar over here in one field, and we're using, for the time being, just two bright bars. So here's the right and the left. So if we put a bar something like that, we get a good response. But if we put a bar, say, further along in this receptive field, and put another bar in the other eye further along, also we get a good response. So this has solved the problem. It doesn't matter exactly where the bar is. Well, if you tried that same thing up here, like we did, it's just a total mess. Like you have simple cells responding and not responding depending on exactly where the bright bar is. So that one solves the problem. And if we know it's a complex cell, so a complex cell, we could just try a dark bar instead in the right and the left side, and it works also. So you get the same thing. So you put a dark bar in there at zero disparity, and you get a good response. And so zero disparity just means that the image in the left and the right receptive field are not offset. But you can find cells that like a non-zero disparity, and so that might look something like this. So you can find a cell that looks something like that. And what does that mean? That means that it prefers a bar that's kind of closer to the end of the receptive field in the right eye. So it prefers a bar that's, at the risk of color overlap, let's put another bar in here. So we put a bar here. So this cell will like a bar that's close to the end of the right receptive field, but it's more like around the middle of the other receptive field. So that's a non-zero disparity. But it likes this, as long as it has a certain offset, you can sort of move it across the receptive field and it will give a good response. And it will work also if you use a dark bar, a pair of dark bars, and if you use a pair of light and dark bars, it won't give much response. So this situation up here, where the simple cell would respond really good, you don't get much response. Response mostly goes away. And so the bottom line is there is a problem sort of like with false matches, but really what the problem is, it's false matches because of the fact that you have simple cells, and the simple cells have multiple fields, and you don't know what field the object is in, and also it's got subfields that prefer light and dark, and so it's going to match something that's dark in one eye with something that's light in the other eye and give a big response. So that's the true, stereo aperture problem. Where does it come from? It just comes from the thing that we talked about from the beginning. You have these small little detectors that are trying to do a good job and detect, where things are bright and where things are not bright. And what does it do? It creates this this mess of a problem. And how do we solve it? Like all other aperture problems, we have to kind of look at, the complex cell has to look across space, do some computations, and then it can come up with a solution to the beginning of the solution to this problem. There's a lot more stuff going on here that we have to sort of figure out, like, is this a continuous, you could imagine, maybe we should look for objects that are sort of smooth in depth. And your system does that. It doesn't expect objects to be randomly distributed in just like a dust cloud of objects at all different depths. It expects there to be kind of some surfaces in depth. And so you probably have like a depth smoothness constraint of some kind. So this is just to sort of introduce all the problems that are simultaneously being solved as you go into the visual system, and very rapidly with very slow neurons.